Grade 12 Physics, Dynamics Note number 10, Vertical Circular Motion. So in this note, we're going to apply circular motion to a vertical frame of reference. So an example of that might be a roller coaster doing a vertical loop. It might be an airplane doing a loop-de-loop in the air, or anything of that sort. So we can draw a picture, just so you have it in your notes. A roller coaster here just doing a loop. The people will turn upside down and feel different forces. One assumption we need to make in vertical circular motion is that the speed of whatever object's doing the circular motion will not change. So it's going to stay the same through the entire loop. So the condition of these problems, which makes them a little more difficult, is we have to consider more than just the force acting as a centripetal force. We have to consider gravity at different points in these loops. So let's try a numerical example. So here we're going to look at an airplane doing a loop-de-loop. So the pilot's going to go through the bottom of the loop and pull his plane upwards. And when he goes through the top of the loop, he'll be basically upside down. So here's an example here. There's the bottom of the loop and then the top of the loop. Position 2 will be the top of the loop and position 1 will be the bottom of the loop. So part A, let's look at position 1. So let's draw a picture of this pilot. What forces is acting on the pilot at the bottom of the loop? We know there's gravity pulling him down, but to make the pilot go in the circle, the chair has to exert a normal force on the pilot. Here, the normal force is acting as a centripetal force on the pilot. There's no other forces. So we know that if he's going in a circle, the net force has to be pointing towards the center of the circle, so the normal force has to be bigger than Fg. Let's put some conditions down. The mass of the pilot is 70 kilograms. The radius of the loop will be 2.7 kilometers. The velocity of the jet will be 225 meters per second. And what we want to basically do is we want to calculate this normal force on the pilot. That'll be the centripetal force. So calling up positive, we have F equals ma. So Fn minus Fg equals mv squared over r for circular motion. So solving for Fn, we get mv squared over r plus mg. When we put the numbers in, make sure we do the proper conversions. 2.7 kilometers should be 2,700. Putting in all the values, we get 1998.5 newtons. So one thing that's often talked about in jets is if the pilot pulls a g-force. To calculate a g-force, all we need to do is compare our Fn to a regular Fn if he was at rest. So the g-force here would be 1998.5 divided by mg, so 70 times 9.8, and that ends up being 2.9 g's. So that would be through the bottom of the loop. Now let's look at the top of the loop. So he's in his chair. The chair is above him in this case because the plane is upside down. Gravity is down, but because the chair is in that position, so will the normal force. It has to push the pilot in that direction. So again here, if we call down positive, so from F equals ma, we get Fn plus Fg equals mv squared over r. Again, solving for Fn, we're going to rearrange our equation, and we find that normal force here is 626.5 newtons. To calculate the g-force, again, we're going to compare 626.5 to whatever the normal force would be at rest, 70 times 9.8, it's 0.91 g's. One final example here. Let's say we're swinging a ball on the end of a string, and it's going in a circle. You swing it as fast as you can, but the ball starts to get slower and slower and slower. You know that if you go too slow, the circle will collapse and the ball will just fall straight down. What we want to do is what minimum speed is needed to keep the ball swinging in the loop. So what is the slowest we can swing it so that it just goes through the top of its arc? So this minimum condition is going to happen at the top of the arc. So let's draw a diagram of the ball going through the top. So there's the ball, there's the top of the arc. what we need to consider are the forces acting on this ball as it's traveling through this point. We know that there's gravity, Fg, but that ends up being it. There is actually no tension. If it's going through its minimum velocity, the rope will just be slack enough that tension will go to 0 at the top. So F equals ma. The only force is Fg, which is mv squared over r. So mg equals mv squared over r. The masses will cancel. The mass of the ball doesn't matter. So here, the velocity of that ball will be root times gr. So the only thing that matters is what planet you're on and the radius of that circle. So we find that the minimum velocity is 2.97 meters per second.